how long these will take, but I do have 7 things you should know about TensorFlow. So I'll probably just kind of high level go through them. They're fun things I've picked up over the last couple of years. Also have a bunch of TensorFlow 2.0 tips. So TensorFlow 2.0 is coming out. And there's a bunch of new profilers and some cool, there's this thing called TensorFlow Lite that is more than just mobile TensorFlow, but it's actually ways to quantize your models down into smaller representations that can be used in the data center as well. So we'll talk about that. And then I also have a sample notebook on differential privacy in AI. So this was, I think, earlier this year, maybe end of last year, TensorFlow team came out with tf.privacy. Differential. It's ways to actually train with privacy as part of the training process. So you're sort of introducing noise into the training. And I can go into that more later. Okay, I think I'll hand it over to Antje in Slack after dark.
Okay, so we just have to
give some context.
Change the share. All right. So shall I try with the with the presentation mode? Better not. We can, make the slides bigger. That makes sense. All right. So as Chris already introduced me quickly, my name is Antje Barth. I'm working at a company called MapR. Not sure if the company is familiar here. Some nod their heads. I'm a developer advocate, so I have fun playing with technology. And part of my job is actually looking at the new technologies out there and playing with it and putting together some exciting demos. And this is actually what we've done and what you see here in a bit, what I'm showing today. It's a combination of really cool of a Slack API, Kubernetes, containers, machine learning AI, PipelineAI, our platform. And we were having fun building a kind of a dating app through Slack. So we'll see that in a bit. Before I joined MapR, I spent many years at Cisco. So a long history in data center and cloud technologies. And now with machine learning and AI, it's going a little bit more in the software and the fun space, I think. I'm also co-founder of a Women in Big Data chapter in Germany, Düsseldorf, where I live. So there are also local chapters, many here in the US, obviously. And that's a little bit my background. And let's see, Slack after dark. So why have I worked on this demo? Actually, our company, they launched an internal demo contest among all the technical folks who could come up with a very exciting and best and fun and inspiring demo. And basically my demo, I called it Slack After Dark, and I show you a little bit what's in there. So basically, it's a mix of a lot of technologies, and probably you're familiar with some of them, maybe all of them even. PipelineAI, obviously, we're using as kind of the machine learning platform. And then a mix of open source technologies. We have Docker in there. I'm using a lot of container deployments, obviously, managed by Kubernetes. Then a lot of the cloud native tools come in there, Istio for some traffic routing. You will see that when we do some predictions between the models and also route the traffic to different models that are deployed. Slack is our UI. MLflow is a piece in there. We're also using transfer learning via Keras. So a lot of fun and exciting technologies, and it's really giving you a good experience if you just play around with those and try to implement something fun. So what is the demo about? So my idea was to put together kind of an end-to-end machine learning workflow, but do it in a fun way, as I said. So I used the Slack API. And for those of you who are not familiar with Slack, it's just a messenger chat service, pretty popular nowadays. And it has a massive API where you can do a lot of good things and integrate and send messages and have applications running in the Slack channels. So I developed basically 2 applications, which you can see here. One is more of a backend service. I called it the AI Monkey. So basically, it's performing all of the data operational tasks. So whenever me being maybe in machine learning or data engineer, I want to test my pipeline, I want to test my models in production, or fix some models in production, see what the predictions are. So anything like more of the back-end tasks, I want to offload to a monkey. So I call it the AI monkey. And then I have a front-end service, which is the customer or consumer-facing service, which is actually Slack After Dark, a dating service powered by AI algorithms. And we're going to see how that works in a bit. So the two services I basically wrote, it's a lot of Python code as well in there, and then just connected through a Slack channel that I'm using to trigger the actions. So a little bit here on the architecture. As I said, we're using Slack as our user interface, just to have something new, something that is not like widely known or used nowadays, to see how easy it is to kind of build those things together. We use PipelineAI as our machine learning platform. You can see here, if you had a look at it already, the dashboard and the different tools and models which are supported. And then I deployed the project in here. Underneath, it's all running containerized. So all the models that get deployed into production, it's all Docker containers. And for those of you who don't know Kubernetes, Kubernetes is a container orchestration platform. So that is used to really manage the containers, also like do some load balancing. So if one host runs out of resources, it obviously reschedules or schedules it on another host. So Kubernetes is really managing the containers. And then we're using MapR, our software, to manage all of the data. All right. So I quickly take you through the individual steps, which I'll show you after that in the live demo, just to have a little bit of a preview and understanding what I've built there once you see it done in action. So what I do as a first thing, I'm going to run a prediction. So I'm using the Slack channel, and I run a prediction, and I pass an image URL to the service. And I implemented something, because it's a dating app, to profile somebody based on the picture. And to make it a fun exercise, I didn't want to do like traditional, is it a dog, is it a cat thing? So for online dating, I thought maybe we pair engineers, non-engineers, like opposites attract, right? It's not 100% perfect, but it's a demo. So I'm passing an image URL, and it's routed to a model that is in production already. And it responds with a prediction, obviously. Pretty straightforward. So we have a request response. We can also show how you can use streaming technologies, what Chris initially mentioned, to implement additional features. So in that case, all of the predictions that are coming from the user base, and just imagine in that Slack channel, it's not only me, it's maybe hundreds of thousands of users of my app, maybe someday. So I can track all of the predictions, which is the live traffic hitting my model, and I can mirror that to a decoy, basically. And what I'm doing here in my case, I'm pushing that to a stream. And the stream persists all of the traffic forever in the data platform. So whenever I need to do a replay of all of the live traffic, the predictions that hit my model, if I want to maybe train another model or like see what happened at a certain time, I can always use this as a kind of persistent replay of all the live traffic that happened. So I'm also doing that as a decoy here. Pretty straightforward until that. What we're going to see is that the model might not be perfectly trained. So what we can also do is using the AI monkey to fix the model. So this is kind of human in the loop integration. So you can, for example, pass all the images which have like unsure predictions, and then give feedback, label the data. So it also gets sent to a stream to persist the information. And then you can basically train the model off the stream, redeploy it into production. And then you could, for example, deploy it as a canary to see how it's performing and compare it against the ones who are in production. And this is really a way to kind of slowly move like more from a batch environment to a real-time environment. And at this point, I might just start quickly my AI monkey. It takes a little bit of time to start up. So I'll fire up my script here already in the background. So As the next thing, I also implemented a rendezvous architecture. And that's probably a more of a newer term for many of you. So it's kind of a design, an architecture pattern, really, how you could implement if you have various models in production. So remember, we fix the model, we deploy a second model into production. And instead of a single prediction, I do a predict rendezvous command now via my Slack channel. It also gets like put in the decoy. But what it does in this case, it queries all the models which are in production. And then you have kind of a function which you can implement to decide which result do I deliver back to the user. And this could be anything you want it to do. It might be the response that comes the quickest, so the cut down latency and has really like a quick response back to the user. Or in my case, I select the one with the highest confidence score. So the highest confidence gets returned, because I assume that's kind of the best prediction in this case. All right. If you want to learn more about the rendezvous architecture, there's a free OReilly book available for download. It's about machine learning logistics. And we also have one of the authors here on site for the OReilly AI Conference. So it's written by Ted Dunning and Alan Friedman. And Ted will actually join us for the conference. So we also have some book signings at our booth for those of you who are at the conference. And yeah, the rendezvous architecture here in more of a general pattern. You see it's a combination of microservices, containers, you have your models. And the idea is really to have an input stream, send it to the models, and then you kind of collect the scores to really kind of decide in a rendezvous service which result are returned back. What I just showed you with a practical example. Okay, and once we've done that, we want to have some fun, obviously. So we're going to run our dating app, and I'm just going to pass, for example, a login with my image. So I'm the user. We have some AI magic. I'm not going to reveal the algorithms here. And using a user database and scoring database, it's going to select a good match, hopefully. All right. And with that, I'm going to sit down here for the demo part. I'll crash my microphone here. See if my AI monkey is listening. That's good. So what I have here takes a little bit of time. What I have here is my Slack channel. So it's an empty channel. And what I do first is I run a prediction command. So what Slack offers, it's called a slash command. So you can develop those as you want. So I just developed this /predict, and I pass the image URL. So let's see if that works. Yep. So what I do here is, as I said, I use Sheldon Cooper from the Big Bang Theory as kind of a sample image. I run a predict command past the URL, and you see that the AI monkey is picking up the task that is supposed to be my backend service. So it runs the predict command, you see the image here, and it delivers back the results from the model which is in production. So this one says 36% engineer, higher probability non-engineer. And excuse the term engineer, I just use it in a broad way. So I know Sheldon is more of a scientist, not really an engineer, but it's more of a broad scope here. So let's assume that prediction, right? I want to tag Sheldon Cooper as being a broad term engineer here in this case. So what I can do next, I'm gonna be the human feedback in the loop here. And I'm gonna say, okay, /fix this model. I pass again the image, and now I pass a label and say, this is an engineer, right? I wanna have this image, this person tagged as an engineer and classified. So I'm gonna run the fix command here. And again, it's processing. The AI monkey is taking the task. It's a backend service. There's a lot of happening. I put in screenshots here. We can have a look at the live deployments also, but just for the ease of use to see what's happening. So the AI monkey is picking it up again. It's processing the command. As a first step, as I said, it puts all the predictions I run into a MapR stream. So you can see here, it's basically the Kafka API we're implementing in the data platform. So it's pushing that to the live data stream. It gets added here. You can see it in the UI. And then a microservice that I developed is picking that up from the stream and is retraining the model. So it takes the image, and obviously you wouldn't retrain on a single image, but imagine like hundreds of thousands of people like relabeling and trying to fix the model. You would then take the new label data, retrain the model, and redeploy it. So we can also store like all the model files in the file system, obviously, version it. So you always know which model got deployed, and you always have the runtimes, etc., together. And then, yeah, as a final step, it's gonna get deployed again in on the platform. And you can see here, those are screenshots from the PipelineAI dashboard. So you can see model V1 first, and then we deploy the second model in production. And you can see that the traffic is also shifting. So far, so good. So what I do next, I want to really see if that picked up the image and the training data. So I'm going to run now the predict rendezvous with, again, with Sheldon Cooper, and see if the results change. So the AI monkey, again, is picking up. And I just deliver here a couple of results for comparison. So as I said, you can decide which result the rendezvous architecture delivers, whether it's smallest latency or highest confidence score. So you can also do whatever you want, like an average prediction. That is actually the one I'm going to use in the profile dating app later, just to like, yeah, get rid of kind of very high or wrong predictions and do an average. But the maximum prediction here you see is 97% engineer. So we trained the model on this image and said this is an engineer. So now and you see here it's coming from the model V2. So that one is pretty sure now, and very confident that this is an engineer now. So you can see the change in the models here. So this is just an easy way to show really how you can use an UI like Slack to interact with your machine learning pipelines and workflows and kind of, yeah, automate things pretty easy and pretty visual here. And then obviously we want to have a little bit of fun. So what I'm doing, I'm logging now into my dating app, just like After Dark. I'm using an image of myself now. I think we had enough of Sheldon Cooper. So basically you can't see the image here for some reason. I'm wearing a Docker shirt, so maybe that's why it's classifying here as high chance of engineer. So it says like average 64%, I'm an engineer. And what also happens in the background, as I said, I'm using a database for user information scoring, matching information basically, which is kind of the core of my operational consumer facing application. So it's putting like the results and everything in the database, and it also runs the matching with information from the database later. So I got a welcome message, and you can see here that actually the Slack After Dark Slack application picks up now. So as welcome, the dating app assigned a profile to you. As I said, 64% engineer, so yay. Try our match function. It's gonna have some fun here. Add you a match. Oh, okay. Who of you is watching the Silicon Valley show? All right, I matched with early. I think it's, yeah, we share the same fashion sense, I think. So this is basically what I just showed you in the slides, what's happening here. And yeah, it's really easy. You can use Slack, for example, to interact with your machine learning models. And I can show you a little bit here in the infrastructure. So it's, as I said, it's running in Kubernetes. And you can see here all the containers. For those of you who are familiar, that's the Kubernetes dashboard. And you can see here the predict, those are the models which actually get deployed as containers. So you have here one which is basically for the model V1, for the model V2. I have a couple of demos running, that's why it's a couple of more here. So using Istio for the traffic routing, etc. We do have Pipeline installed, as I said, as the machine learning platform. And you can see here model V1, V2, which I'm using, the models which are deployed, traffic routing, etc. And the other thing I want to show you is the MapR platform. So the nice thing we can do here is actually it combines a file system with streaming capabilities and a NoSQL database. So I got here a stream, Slack After Dark, with various topics. And this is basically where I push all of the data. So you can see here it's growing in size. So I have one topic, and for those of you who are familiar with Kafka, it's using the Kafka API, but the platform is basically managing the data and providing this publish subscribe model. So we have one here where I send like all of the predictions as a decoy, basically, to be able to replay the live traffic at any time. And I have a second one, which is actually used as the training data stream, where I read off when anyone provides feedback to the models. And then it's the same platform where you can also have tables. So I also here have a NoSQL database and tables for my Slack After Dark, like functional database where I put like the user scores and the matching that is happening. So MapR is also, for example, available as a community edition if you want to have fun and play around with it. It integrates into Kubernetes. So it's also playing the persistent storage when I store the model files. And you can use it, like, for example, for versioning, etc. All right, so let's switch back here to the slides. Any questions so far to the demo? Yeah.
So the question is, containers running in Kubernetes, how is it getting access to data in MapR? Is it using Kafka or is it mounted?
So we have various ways to integrate. So we do have an integration purely for the Kubernetes part. So we can mount via CSI, a storage container storage interface. So it's really being the persistent platform. Or in single containers, also if you're not using Kubernetes, we have integrations in Docker containers, for example. And it's basically a little client which you install, which authenticates. So you also have like security concepts. So it authenticates against the data platform and sees if the container and the applications are really authorized to access the data. So we can like push that authorization concept also into the container world from the data platform. So it's really giving you like one place to manage the data. And yeah, so we do provide like all of the open APIs. So if you want to use streams, for example, it's the Kafka API. The streams get stored and the data in the platform, but it's the open APIs. We have REST, JSON, OHI interfaces for database, etc. So for your applications, it's not much of a difference really, because they have the standard APIs, but it's giving you and your IT and company a kind of a way to manage the data in a central location, regardless if it's the machine learning, the AI development, or the BI team in the company. Yeah.
Could you please go over the random architecture just a little bit? This first time here.
Yeah, sure. So actually, I think Ted Dunning kind of brought this term into discussion, and it's really kind of, as I said, a design pattern. Yes, thanks. So what you would do is really, it's kind of helping you to work out the data logistics, because in many times, and maybe you can agree or not on this, you would like to really spend your time as a data scientist on developing the models, improving the models, etc. But reality shows that most of the time is, how do I integrate into systems? Where do I get the data from? How do I get the data flow going here, etc. So it's a lot of like data engineering and data logistics, which you spend like most of the time with, rather than developing and improving models. And this is what the book talks about general concepts, machine learning logistics, data logistics, how you can improve them. And his thesis is, if you're using like streaming architectures in combination with microservices, it just gives you a bigger flexibility in implementing that for models which do like prediction. So it's a request response in most of the cases. So you have a request which gets inserted into an input stream. And then you can replicate the stream and send it to different, like in the sense of publish, consume, to consumers. So your models would be the consumers of the stream. So it's very easy for you also to like spin up the model 4 or 500 to that architecture and just add it as another consumer to the input stream, right? And thinking in those concepts, it helps you to build this data logistics infrastructure. And then you kind of decide, as I said, in a score or whatever you call it in another stream, you collect the results from the same prediction, and you decide based on a function you apply, which result you want to return to the end user. Is it the one that comes in first because you want to really improve customer experience and have the quickest response that you can get back, or you want to rather go for quality and say, like in my case, I pick the one with the highest confidence, whatever you want to do. And this one gets put into another stream where then the user or the requester listens on and gets the response. So this is basically a general concept how you can build or improve data logistics.
I know with microservices sometimes there's a time lag. Is that an issue with this?
So the good thing is with the streams, they have cursors when you read. So you could even, as a consumer, so if you're waiting for the response and there's kind of a lag or you lose internet connection for some reason because I know you left the reachability zones, whatever, on your device, you can always pick up reading from the stream. So you never lose any of the data. So whenever data is written and pushed to a stream, it's there. And the consumer applications, they have a cursor, so a position where they read from. So whenever there's a time lag or whatever, they just resume from their cursor. So they always read in the right sequence whenever the data arrives and you're able to read. Yeah, no, that is why streaming architecture is a good idea maybe in some cases, because you can work around those, yeah.
If it helps, I still don't understand the term, like why it's called that, but it's like model ensemble.
Yeah.
There's a part where you can analyze the inputs coming in. It's more conceptual, right? But and see if those inputs like match the same distribution as what these models are trained on, and then you can kind of get some feedback.
Yeah, so you can implement it, as I said, like whatever use case you might have and think this might help in improving. And as I said, it's a free ebook for download at O'Reilly's from our website. If you just Google for Machine Learning Logistics by Ted Dunning and Ellen Friedman. Yeah. 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 Sure. Yeah, it's not like a huge. More questions to the demo? Or
When you go through models to the source, is it just a straight average?
no, you're collecting you're first of collecting all of the results basically, right? Because you want to see what the models return, and then you can provide a scoring system or whatever you want to do, right? And then basically the rendezvous is kind of a service, another microservice who works on top of those scores and decides what to pick. So this needs to be implemented by you because you have the logic which one you want to pick. So you just need a way to kind of score the results or like put it in priorities or ranking or whatever you want to do, right? And you obviously always want to be able to kind of track back in case there's a question coming up later why this got picked as a result, you know? So you can always trace it back because it's always persisted in the stream. So it's always a good way also to kind of show like why the result got replied. Yeah, in that way. All right. So yeah, just to wrap it up, and I guess Chris can talk a little bit more and then better about that part. Why I chose PipelineAI. First of all, it's a great framework running every hardware, every cloud here. Nice dashboard for the life cycle. I could implement the traffic routing to model 1, model 2 here. Generate the optimized runtimes for the models. So especially when I deployed the model V2 with the newly trained data, we generated a new runtime that is stored in the underlying file system. We could version it, etc. And do the shadow, the canary rollout via the application, the percentage-based rollouts. Yeah, and I think Chris will give a couple of more updates to this one. To wrap it up, as I said, just as a little bit of overview, the MapR platform, as I said, the nice thing is we integrate file system, real-time streaming, and the database in one software. And it integrates in all of the tools. So if you're using PyTorch, TensorFlow, Spark, etc., other services, maybe if someone from the BI team uses more of the traditional, like the Spark or Hadoop-based analytics, they can all run and access the same data. So you don't have to call your IT and say, well, I need more data to train my models. You can basically integrate securely, authenticate it, etc., and use this as kind of the central platform, yeah, to manage and control the data sets. Integrates into containers nicely, cloud native Kubernetes. It's bringing the security, etc. It really helps to kind of, if you think of it as Kubernetes for data, if Kubernetes kind of abstracts the applications from the underlying infrastructure and helps you in kind of deploying applications described in like the files you're developing there, MapR kind of helps you to do the same for the data. So it abstracts the data from the underlying infrastructure, and you can decide where you need it for which use case and application. So this kind of a thing, we sometimes call it dataware, or Kubernetes for data. I think it's also kind of resonating if you're coming more from the cloud native world. All right, that's it. If you're interested in learning more, I'm here for the conference as well. So if you see me, you can always just come by, ask questions, or we have a coffee together. One of my colleagues, Jack Norris, he's speaking here at the conference. He has a talk about unlocking AI value at scale on Wednesday. Is it tomorrow? Or the other day? 2 days. And yeah, and Ted Dunning, as I said, is here. He does book signings. And yeah, you can win some fun stuff at the booth. So if you're interested, Star Wars Lego, yeah. So just come by or grab me here after the meetup. All right, thank you very much.
For those of you that like just showed up, so we started a bit early. It was 6 o'clock, I think, was the time on one schedule, and then it was 7 on the other. But we are recording it, so we're going to post it after. And we still have about 2 or 3 more parts. I'm trying to share. Okay. So thanks, Antje. That was great. In terms of open source alternatives, there's like Ceph. Yes, I don't want this to be like a product pitch. There are like open source versions of all these tools. The thing that like MapR provides, of course, is the security, the enterprise security, and all that good stuff. And yeah, I was actually pretty surprised at how easy it was to convert, because the first version of this was all Kafka, and then because MapR supports like Kafka API, Python, Java, all the different APIs, we're able to plug it in pretty easily with minimal code changes. All right, so let's see, we did that. Did this. Here's a blog post that shows some of the same images and some of the same concepts as well. You could search Medium, PipelineAI. I want to show, so I mentioned at the beginning that I spoke at the Redis AI Conference recently in San Francisco, and I had started working with these guys about a year ago and was trying to talk through how they can integrate Redis with TensorFlow. So let me show you. All right, so who here? Anyone use Redis? Everyone use Redis? Yeah, kind of. So Redis is, if you think of like Memcache, like ++, it's fully distributed, and it's used for like lots of like gaming companies that do leaderboards, and yeah, just think of it like a massive cache. So this should be connecting directly to the Redis cluster that's running within Pipeline. So that's behind the scenes. So there's this special API that they've created that's an extension of the Redis Python API. That's called Redis AI Rai. We create a client. We give it the host. That's the normal stuff. We're actually creating a tensor. So up here, we could take a look at the imports. It's this Redis AI client type, D type, tensor, blob tensor. These are all TensorFlow terms and like machine learning terms. So this is a simple like NumPy array that we're setting into the cache. And we're pulling it out, and this is a tensor that can be converted to and from TensorFlow's type system. We're gonna put in a blob here. In a sec, we'll do some images. Let me just get to the images. So we're actually gonna load in the ResNet 50 model into Redis, and then start to pass data into Redis and have the predictions come out on the other side. So these are the predictions. This is a JSON file that basically maps a number to a category. So these images that we're passing in are going to be fun images. It'll be guitars, it'll be cats, whatever. And this JSON file maps the output of the model to the actual class. So let's see. I think I already did that. All right, so here we're calling a Redis command, AI model set, and giving it the model, passing in a bunch of inputs. That supports GPU as well too. It'll then load the GPU version of TensorFlow. Tell it the inputs, tell it the outputs. And then this is something too that's cool, is like, so beyond just the model itself, you could actually pass Redis scripts, like Python scripts, to execute. And so this is good for like pre-processing data, or if you want to post-process your like results and convert them back to JSON or CSV, whatever you need to do. Okay, so here's a picture of a cat, cute little cat. We're setting it as a tensor, as a blob. And we're getting it back out. So it's one row, it's 224 by 224 by 3 colors. And now we're actually going to execute these and make the prediction. So the prediction came back in about 2 seconds. The result was 281. We're going to use the JSON to convert it, and it's a tabby cat. And I think if we run this again, like the model's loaded and it's much, much faster. All right, and then we got a guitar. So the output there, 402, it's an acoustic guitar. Yeah, showed it up there. And then this was my favorite. I threw this in for the creator of Redis, who was like sitting in the front row. I have a picture of him. He's this crazy Italian guy. And let's run his picture through. And it's barbershop. So that's the ResNet 50. Years and years of research went in this model to predict this guy needs to go to the barbershop. All right. So that's Redis AI. It's super simple to set up. It's just Python API, Java API, supports PyTorch. I'm more familiar with TensorFlow. It supports Keras. Basically supports like any model that you can export out of TensorFlow, and then you could slurp it into the Redis runtime. Okay, so this next part's I'm going to go over a little bit quickly. These next two actually, so 4 and 5 kind of tie together. All right. And this is some slides I put together on the train from DC last night. So this is like early version. Who here has gotten the famous out of memory error with TensorFlow? It's like the worst error ever, right? It's like I have all this memory. I have these huge GPUs, 16 gigs of RAM. My model can't be that big. So what do? So typically you have too many parameters, right? You're trying to learn too much. And there's a few ways to simplify your model. One common thing people don't think about much is that you can actually achieve the same amount of learning potential with 2 3x3 convolutions that are stacked, like one after another. So this concept is called stacking. Versus just having one 9x9. And so this is 2 3x3s. This ends up being much, much smaller number of parameters. So that's like something to think about if you're designing your own neural architectures. Typically, you're just reusing somebody else's or starting with somebody else's, like Antje, using the transfer learning. Which model did you use?
I think it was the mobile net.
Oh yeah, mobile net, yeah. The other thing is TensorFlow has this data type called bfloat16. And what we're doing is we're able to like represent each parameter not as 32 bits, because that actually is quite a bit. That's 4 bytes to represent one parameter that we're trying to learn, and there's millions of these parameters. Now we can reduce it down to 16 bits with something called bfloat16. And the reason why this is different than float16 is we're actually storing more of the exponent. So I should probably make that bigger, but bfloat16 preserves more of the exponent, and float16 shrinks that up. So the end result is your dynamic range sort of increases, right? And with a larger dynamic range, you can start to like represent more with half the number of bits, or the same number of bits in the float16 case. So bfloat16 kind of popped up, I don't know, TensorFlow 1.0 or 1.2, something like that. And what you do is you can actually mix and match. So TensorFlow 2.0 has been written so that you could sort of interchange bfloat16s with float32s. And if you want to do your like matrix multiplies with 16-bit, right? Because multiplying two 16-bit matrices is much, much faster than 32-bit, but store the result in 32-bit. And then you would add with 32 bits, because that's a lot. That's less computationally heavy, adding versus multiplying. Typically, when people run out of memory, they're trying to use the GPU on their local laptop or on a small, cheap server, the old NVIDIA K80s from 4 or 5 years ago. And TensorFlow 2.0 has a much, much cleaner like distribution strategy. They're still not quite to the point where you could distribute across multiple servers, although that's what I put there. It's actually, the first version of the mirror strategy is multiple GPUs on a single machine, or in a single cluster of just GPUs. So yeah, check out, it's tf.something mirrored strategy, I think it is. Also, TensorBoard in TensorFlow 2.0 now has a new profiler. And this is super handy if you've ever tried to like debug your own code, just normal performance stuff separate from AI. You want to be able to see how fast your code is going, where are the bottlenecks, what's actually causing the problem. And so TensorBoard, the cool thing about the profiler is it doesn't stop at just CPU and GPU. It actually extends into the input pipeline. So I'd say 9 times out of 10, the types of performance bottlenecks that we see are the inputs, right? Like just pulling data from disk and doing it in a like not so efficient manner. So if you can pull in parallel, for example, from 8 different disks or from Google Cloud Storage or Amazon, like S3, this is very, very powerful, and you can essentially scale up as large as you can. So yeah, like, let's see. So why is my training job slow? So this leads in, yeah, the input data is loading slowly. This is almost always the case. There's this concept called parallel interleave that can optimize. It's essentially, it's pulling data from disk or from like remote or like cloud storage at the same time that it's utilizing CPUs and GPUs. So think of it like it's doing things in the background. If you're familiar with like asynchronous programming, network programming, very similar concept. Also, parsing the data tends to be very slow, and you'll see this in your profiling. If you're familiar with Spark, Spark favors the file format called Parquet. And Parquet was created because of Spark workloads, because of analytics type workloads, right? Large sums, large aggregations. And so there's something similar called TF record, and there's ways to actually go between like Parquet and TF record, CSV and like TF record. So the first thing we do is tell people, have you explored TF record? Yeah, try out this format. It's very parallelizable, and most of the new Keras APIs, actually all of the new Keras APIs support TF record. Oh, and so I should mention that like TensorFlow has moved over to Keras. That's the main like high-level API. So if you hear me say Keras, it's sort of interchangeable with TensorFlow. Also, if you're using TensorFlow within Docker, this burns people all the time. So Docker is super well known for not properly representing the number of CPUs that are actually on the system. And so if you're not careful, you aren't telling TensorFlow how much power you have because it's running in this container and it's only seeing a fraction of the CPUs that are actually available. And so there's a couple ways to solve it. The most obscure but the most effective way is by setting these intra-op, I think it's intra-op parallel threads or like parallelism threads. If you just search intra-op and inter-op, these are internal thread pools within TensorFlow. And if you can manually set those and just like jack up the counts until you can saturate that like underlying. And that's really more of a Docker issue than it is a TensorFlow issue. But this is something that like not many people know about. Also, if you haven't already, explore something called batch normalization, explore dropout. These are regularization techniques. These are ways to speed up convergence of your models during training. They work in most cases. I remember doing a talk at, I think it was OReilly AI London, and I had done this whole talk on batch normalization, and the person after me his whole talk was how batch normalization doesn't work. So it was like we were exchanging microphones, and I was like, I should probably talk to you afterward. Yeah, because he had a lot to say. Okay, and this is more on GPUs. I see this question a lot. It's on Stack Overflow almost daily. I have my GPU. I have a cluster of GPUs. Why is training not 10 times as fast? I'm paying 10x for these GPUs. There's a few different reasons. Typically, you're not saturating these GPUs. Typically, you're spending lots of time pulling data, and that GPU is actually being utilized 3% or 2%. Right? These things come out in the profiling. So either increase your batch size, use the parallel input or data retrieval techniques. Also, when you're in Docker, there's cases where, once again, you're not telling Docker the true number of GPUs that you have. And this is very, very easy to miss. And you can kind of see it when you start your job because it'll start saying which GPUs that it found. That's a lot easier to detect than the CPU one that we spoke of on the previous slide. Also, if you're using Intel KL, which you should be if you're on CPUs, there's a couple parameters that you should know about that are sort of internal, and I can't remember the exact details, but it has something to do with the wait loop and ways to, with different chipsets and different workloads, these parameters come in handy. Okay, and then CUDA 10, if you've ever seen this classic import error, lib blast not found, or yeah, the lib qblast. This is TensorFlow saying you've told me to use GPUs, but I don't have the actual driver, right? Or I don't have the proper imports for this. And this is in CUDA. So before CUDA 10. Yeah, so TensorFlow uses CUDA, and that's a C library provided by the NVIDIA folks that's optimized for their GPUs. For CUDA 10, it was very difficult to do dot releases within, or to stay behind on. So say that you built your Docker image with CUDA 9.1, and the underlying machine upgraded to 9.2. Now you have a mismatch, right? Because what you're doing here is poking holes through Docker, or poking holes down, and using the underlying CUDA drivers. So with CUDA 10, they've split, and there's now separate. There's backward compatibility within major releases, so that you could version one and not have to version the other. The short of it is you'll see this error less if you're and TensorFlow 2 only supports CUDA 10. I think TensorFlow 1.13 supports both, which is actually more confusing, but switch to CUDA 10 as soon as possible. Yeah, anyone here use TensorFlow serving? So TensorFlow serving, this is a classic yeah, so why? So I've deployed my model, and it's just predicting poorly. I can do better if I just do batch prediction. So like TensorFlow serving is a way to serve online models from TensorFlow. So you could get in JSON, convert the JSON into NumPy array, and then predict, and then convert it back into JSON and then return. So think of request responses. If you're doing batch predictions, TensorFlow serving is like generally not what you want to do. This is the C library actually that like Redis AI embeds. It's called lib, it's like lib TensorFlow or something. So typically what we see here is people train on a CSV of a particular format. And then when they pass the data in, they tend to not get the format exactly correct. So this is pretty easy to detect. It's kind of the first thing that we look at. Are you like sending in the same inputs? That second bullet point is different distributions, different normalization techniques. During training, I like normalize between 0 and 1. But when I take that like request, the application team sends me like this request, and it's between 0 and 100, and this just doesn't fly. So like Keras has this nice little bundle of utilities called TF Keras utils, and there's an old TF like utils too, but this is the recommended way. And you will like almost always see normalize as the first thing coming in. This is where you would standardize. This is where you do all of your sort of pre-processing. Also, yes, as Antje was, so she was like suggesting, if you have multiple models, these are classically called ensemble techniques, where you have like multiple models that are predicting and taking maybe the highest confidence, averaging. This is actually a very, very powerful way. And what you want to be careful of here is when you do have multiple models that are part of a single prediction, make sure that you have timeouts set up super aggressively. If there's one sort of slow like model that's been deployed, now the whole system slows down to that weakest link. There's this new, the like pro tip here is there's this new, I guess, sort of batch of startups happening in San Francisco just in like the last 6 months. A couple people left Uber. If you're familiar with Uber Michelangelo, those guys left not to work on Uber Michelangelo, but actually to work on this concept called feature store, right? So feature store or feature database is sort of this like reusable pre-processed or pre-transformed features. So when you're like typically when you're like training models, you're combining certain features, age, right, like geolocation, yeah, things like that. And you don't always know what the best combination of these features is. So you can start to borrow from other people's. So think of it like a database of pre-processed transformations. Or what we're seeing now is flow. So we would see like the normalization and the CSV to like TensorFlow code already that's been checked in for the rest of the organization to use. So how this ties into TF serving is, what you want to do is make sure that those feature transformers are inside of your TensorFlow graph. And like you don't want to rewrite those over and over. So you would talk to the people who train the model. Hopefully they've stored the way that they've transformed these features somewhere, and then you can reuse it in your like TF serving graph. All right, stick to the yeah, actually register because it's the very first thing that we do is just tear that out. There was a period in time where people were putting in, and Pipeline does this too, where we were putting in Python snippets external to the TensorFlow graph execution. And that's a disaster in terms of performance, because you're doing some transformations in Python. Now you have to maintain a separate Python script. Maybe the format changed, the transformation changed. Then you would pass it into TensorFlow serving, and then you would have to get the response and go through. And there's just way too much going on there. So TensorFlow serving now actually has an HTTP like implementation. seemed to take about 2.5 years for that to actually come through. It was like the most requested feature ever because gRPC is a little bit wonky and not readable. It's super fast, of course. It's a binary format. So the point here is push your feature transformations into the actual TensorFlow graph being used at inference time using the feature stores potentially. There's this super easy way to turn on batch predictions with TensorFlow serving, and this will take a bunch of matrix multiplies in. You wait 10 milliseconds, 20 milliseconds, get all the separate like predictions that are coming in, pass them all to the GPU or to the CPU or to the TPU, and make one big matrix multiply, parse out that result, and send it back to all the different clients from across the world making these predictions. So this is an obvious turbo button. This is very, very high load stuff. TensorFlow sometimes stops responding. And it's not really TensorFlow serving's fault, we're just hammering it, right? So there's times when, and like this goes back to my Netflix experience where you wanna put in fallbacks. So if your server is not responding within 10 milliseconds, just start returning a default. If you're doing like recommendations, just return top 10 movies of all time and then move on. That'll let the TF serving cluster settle down, and you can also give time for that cluster to scale out. The other good news, this is the other feature that was sort of like sorely lacking within TensorFlow serving for about 2 years. They finally added Prometheus-based metrics, so they're exporting metrics now inside of TensorFlow serving. And so that was the other reason why we had Python and Flask involved before, so that we could actually get timings, because there was no way to get timings. Once that request went into TensorFlow serving, we had no idea where time was being spent. So they like export a whole bunch of stuff now, so you can start to trigger off this, start to look at the actual latencies. Once latencies get to a certain point, start to scale up. Okay, privacy. So GDPR is on everyone's mind. Is it? Is GDPR on your minds? You guys think about it? So what are the obvious ways to ensure data privacy? So we're all familiar with, well, let's just remove the sensitive data, right? The PII data. Well, that doesn't always work, because that's usually the data that we're trying to model on, right? These are our features. If we start to null everything out, we're going to lose the ability to model and to learn what we're trying to learn. So, so that's not enough. And if you think about it, if you expose a model, or like deploy a model, I shouldn't use the word expose, but if you like deploy your model, and now hackers can come in and start to pass just random inputs, and they can get outputs. And so they could start to actually reverse engineer this model. And they can start to reverse engineer the weights that are being used, especially as more and more people are reusing the same models, right? Coming out of DeepMind and Google. So the architectures are pretty well known, and there's not much variance there, but these weights can be learned. So what's the response there? Well, let's introduce noise during training to kind of slow down the hackers, right? But this noise can be learned. So there's this concept called differential privacy. And this is what's in tf.privacy, and I think I have a working example here. I want to get a poster of that guy. Cracks me up. He's like the coolest guy. Let's see, privacy. And yeah, these are all available. Let's see. Oh yeah, I have a notebook here. Oh, dating with scans. Yeah, we have so many like dating examples. Pretty funny. All right, so this is with, yeah, so from privacy, and I think this is actually an earlier version, but it's the same thing. Now it's under tf.privacy. But there's ways to tune how much privacy you actually want to achieve. And if you ask anyone how much privacy are you like looking for, they're going to say 100% privacy. There's a struggle between privacy and accuracy and speed. These are the three things that we're starting to see people making decisions about. Like whenever you want to increase accuracy, you usually end up suffering on performance. Whenever you try to increase privacy, your accuracy starts to go down. And so there's this privacy budget, and like the way that they call it here is the accountant. Yeah, so you would like this, the accountant in the room. And the short like answer here, the short description is you can calculate actually like the amount of privacy, the budget that you're able to sacrifice. Say I have 5% of my accuracy I'm willing to sacrifice for this particular. And yeah, there's this index, the like RDP order, some other stuff here. See there. And then this is a Keras model that's being trained with the privacy turned on. See if I can just go through it. So the current epsilon, yeah, so you guys can go like check that out. But okay. Yes, I was in a like privacy talk a few months ago, and there was a guy sitting in the front row. We had a privacy lawyer that was speaking about GDPR, and this guy worked for an insurance company that was making, or no, it was a credit scoring company. It's the classic, like, you know, and what he realized after the talk was that his entire startup was completely doing illegal things. And his, like, yeah, his whole job, he like wanted to quit the next day. He's like, there's no way we could actually release this product. Or they would have to sacrifice, you know, all of this for high privacy. Let's see. I have one more bonus here, and I was working on recently. Otterbot. This was a fun thing. I was in a workshop and I chose something ridiculous. So if you guys have heard, there's this class of like neural networks called GANs, generative adversarial networks, GANs. And StyleGAN came out. This is from the NVIDIA folks. These are actually generated completely, so these are not real people, right? And they look surprisingly real. What are some of the differences, Antje? Yeah, you were telling me there's ways to figure out.
Yeah, so there was an article discussing how you can detect if it's actually an AI-generated person or not. And they're like small things, like on the latest pictures, like the AI doesn't get sometimes the earrings correctly, or the ears look weird, or the teeth look weird, or the haircuts. So whenever you see like a lady's picture with a super weird haircut, you think that woman would never go out of the door with that haircut. So you know, picture. And you can really spot them too. Like sometimes, like the ear is like double here, missing on the other side, and things like that.
Yeah.
Teeth are sometimes like weird. Yeah.
So yeah, generating these images took, I think I did about 13,000 in an hour on a pretty like medium-sized GPU. So this is, you know, kind of fake news for dating kind of thing, right? People can get. So that was what I was trying to prove here is, this is using, what was the other thing? Let me just run it, I guess. Oh no. Okay. Oh yeah, and then we were doing image search. So you would put a picture of yourself and see who you matched with in this fake data set. So this was a girl here, and this was sort of pairwise distance, similar people. And then there's this concept of like eigenfaces. If you're familiar with like eigenvectors, that's essentially what we're doing here. So this is, of all the people, let's see, yeah, how did we do this? We made recommendations based on image similarity. And then we combine them all into sort of an average face. So what is the sort of eigenface, the average looking face? And these are the top 10 eigen like vectors here. You could start to see, noses come through here and creepy looking eyes and stuff like that. But yeah. So coming to a dating site near you. All right. The last thing here is TensorFlow Lite. So very, very powerful. I talked a little bit before about floating point 16. So when I had mentioned bfloat 16, that was at training time. So I was actively choosing use 16-bit. Sacrifice a little bit of accuracy during training, but make my training process faster, the actual time to train, the time to converge. Yeah, so backing up to that, the reason I would want to speed up training is whenever you're handed a new data set, you're trying to figure out this data set. You're trying to learn the hyperparameters, you're trying to understand distributions. And the faster you can get through training, the faster you can learn. So what people typically do is they train at 16-bit, they learn the data set, then they back up to 32-bit, or they just stay at 16-bit because they're already getting 97% accuracy or whatnot. So this is post-training. So I've got a model, and it's 20 gigs, or let's say, yeah, 20 meg is the example. I think MobileNet. And while this could fit into memory, you probably want to reduce. These are small devices. Phones are actually pretty large these days, but think of small sensors or small cameras. I'm trying to fit this, and I only have 32K, let's say. Small little Raspberry Pis or edge TPUs, whatever. So there's ways after training to take that model that's been trained at full 32-bit and quantize it down into 16-bit or even 8-bit. And so this is pretty powerful because you're not only making this model smaller so that you could deploy it, but you're speeding up the multiplications. You're speeding up the actual predictions. And yes, you'll lose some accuracy. So second bullet point, my quantized model is not performing as well. Maybe I lost 10% accuracy, maybe I lost. So now there's ways to actually quantize during training. So that's where you would back up and say, all right, well, this technique worked post-training. Let's see how we could do during training. And what TensorFlow does with one command, one Python API, it'll insert these sort of min and max, sort of fake quantization nodes, they're called, into your execution graph during training. Okay, and so now I don't want to load my entire TensorFlow runtime to make one prediction, right? So yes, I'm addressing the model is slow. So this is, my model predictions are slow is what that should say. And what's happening here is we have to load the entire TensorFlow runtime with all these operators and all this, the support for different hardware. But really all we want is operators to fulfill our actual prediction. So think of linear regression, for example. This is only 5 nodes or 6 nodes. If you have to load the entire TensorFlow runtime, this is huge. And so there's this thing called TensorFlow Lite, which at one point was called TensorFlow Mobile, which they wanted to generalize from just mobile, because this is also very useful in the data center behind big servers. So TensorFlow Lite is a runtime, but also can do that top part where it quantizes. But it's also, it's starting to permeate through hardware companies now. So for example, the NVIDIA folks have bindings for TensorFlow Lite. Multiple companies are starting to hop onto this sort of lightweight runtime. And the way that they're doing is through these things called delegates. And this is a first-class citizen. You can Google delegate TensorFlow Lite, and this is places where hardware companies come together and extend these sort of base interfaces. In TensorFlow 2.0, in the context of being able to evaluate the things that you're trying, these performance optimizations. There's something called TensorFlow Accuracy Library. You can run this against your TensorFlow Lite version of your model, and it'll tell you how shitty it is or how good it is. So keep that in mind. That's a nice little tool to have. I think that's it. Any questions? Ooh. Yeah. Questions for me or Antje?
Apparently, some people have encrypted data and then done work on post-encryption.
Yeah.
I mean, I imagine every pixel data set encrypted.
Yeah, yeah.
So the encryption is even across everything else, the same encryption.
And TensorFlow even supports encryption, right? You can, like this is not my area of specialty. I'm having a meetup in, I think, June, like July, back in San Francisco. Yeah, so we record all this. There's a startup that actually came up to me after a previous meetup and said, hey, we're actually focused on this kind of stuff. And yeah, that's exactly what they're doing, is faster ways to encrypt. Yeah, and it's a way to give your model to somebody and be like more confident that they're not going to crack it or see the actual architecture or see the weights. The problem is the runtime has to support it, otherwise. So on the fly, they're actually decrypting just parts of it. And I think the other part of his company, and I can't remember his name, but is the federated piece, where they are making parts of the prediction over here, parts of the prediction here. Weights are stored across the cluster, and then they come together for the final prediction. Yeah. 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 The Twiml guy had like a whole section on differential privacy. Yeah, he can explain it a lot better. Yeah.
The encryption is some sort of RSA key, where it's just some kind of.
Yeah, the differential privacy is based on like cryptographic techniques. So when you read the papers on that, some of that will be familiar. The encryption part is like literally just on the fly RSA, I would assume, right? Yeah. I don't know too much about it. Yeah. But the differential privacy stuff definitely does come from. And the way that I always remember how differential privacy works is so let's say I'm going to poll everyone in the room and say, who did you vote for? Right? Did you vote for Trump? Did you vote for Hillary? And you don't want to say because you might get fired or killed or something, right? These days. So I would ask you, and I would say flip a coin, and if it's heads, tell me the truth. If it's tails, you may or may not tell me the truth. And so there's this, what's the term? There's sort of an indirection is kind of how I think about it, where I'm not always confident that what you're telling me is the truth, but across a whole number, if there's thousands of us that we're polling, I can estimate and subtract out that probability at the end when I'm making the prediction. So if I get a hold of one single, or if I reverse engineer the model and I learn that you, every time I pass in you, I get Trump, it's not always the case, or you're not guaranteed. There's some term for it. Yeah. Yeah, yeah. There's an extra step, beyond just introducing noise. Kind of the first step is to just add in random noise, but you could figure that out.
But isn't that counterproductive because it's really killing the accuracy?
Exactly, and that's the trade-off. That's why you would these models when you train with differential privacy, you're passing it a different optimizer that wraps your stochastic gradient descent optimizer, and it's now the differential private stochastic gradient descent, and there's an extra parameter that you pass, which is this budget, this privacy budget, and you have to play with that, and it's a hyperparameter essentially. Yeah, and then at the same time you're battling with the legal team, and you're trying to figure out. And then the application team wants us to be faster, and the CFO wants the number of servers, the Amazon bill to come down. So, yeah, any other questions? Oh, and there's a community edition for MapR. Yeah. Cool. Yeah, thanks for coming.